Okay. So we're going to be solving trig equations for two different classes. It's just a big enough section. So we're going to do them today, and then we're going to have our test on Tuesday and not have class, and then we will finish this section up on Thursday next week. This tends to be a little bit of a tough section for people because we have to be able to see the algebra through the trig. So I'm going to do a lot of substituting, kind of off to the side work, so that we can try to see the algebra. So just some strategies that we want to take when solving trig equations. We want to decide whether the equation is linear or quadratic in form so we can determine the solution method. So that's the beginning of trying to see the algebra through the trig. If only one trig function is present, you're super happy about that. All right, like this first example, sine of x plus 2 equals 3. This is going to be as easy as it gets. One trig function is present, you're just going to isolate that trig function. If more than one trig function is present, and what I mean by that is like a sine and a cosine, a tangent and a secant, that there's not just one function, you're going to rearrange the equation so that it equals 0. You're going to try to factor it and set each factor equal to 0 and solve. That's just us using our zero product property. Now, if the equation is quadratic in form but not factorable, you're going to have to suck it up and use quadratic formula with these trig functions. It's just instead of x being equal to whatever, you're going to have like sine of theta equals whatever. You might have to use any of our trig identities to change the form of the equation. It might be helpful to square both sides of the equation first, but remember, algebraically, anytime you raise both sides of an equation to an even power during the solving process, you have to check for extraneous solutions. So we'll kind of just go through a bunch, and we will look through for the algebra through the trig. So we want to solve our equation for the exact solution over the interval 0 to 2 pi. Anytime you see exact solution, that tells you you want your answer to be in radian. Also, notice the interval that they gave you, that is also in radian, so we know our answer should be in radian. If we have just a single trig function, you want to isolate that single trig function. I'm going to subtract the 2 over. Sine of x is equal to 1. We're trying to solve for x, which is inside the argument, so that's equivalent to the angle. Anytime we're trying to find the angle, this is where our inverse trig function comes into play. X is going to be equal to sine inverse of 1. We want to find where from 0 to 2 pi, so that's the whole unit circle, where from 0 to 2 pi does sine equal 1. Now, this is slightly different from what we did on Tuesday. So on Tuesday, when we were doing our inverse trig functions, we kept talking about what quadrant these things were defined in, right? So like tangent, what angle between negative pi over 2 and pi over 2 does tangent equal 1? For cosine, we were looking between 0 and pi. Now you'll notice in the directions, it does not give us an interval. It just says find the exact value of y. So when that's the case, you're using that pure definition of your inverse trig function, and you can only select 2 quadrants, the 2 quadrants where we are 1 to 1. In this section, because they are giving us an interval, we can go outside that pure definition of the inverse trig function. This is why I put it on a separate test. I used to have these two topics on the same test, and people confused them all the time. So on the test that you're taking on Tuesday, when I asked for the inverse, when you're using sine inverse or something, you should only be giving me one answer. But then on the next test, our Unit 4 test, you could be giving me multiple answers. So I just want you guys to keep that, very, very separate. All right, so we're looking where on the whole unit circle does sine equal 1? Well, that only happens one spot right here. Sometimes it's one, sometimes it's more than one spot. Only happens at one spot, so we're going to get that x is equal to pi over 4. Questions on that?
Isn't that pi over 2?
Oh, yeah, thanks. All right, anybody else? Bobby's inside. You should be too. All right, let's look at the next one. All right, so this next one, you'll notice that we only have cosine. However, we have cosine squared and cosine to the first. So this is one that is quadratic in form. Now, anytime we want to solve a quadratic equation, we set it equal to 0, and we're going to either factor it, or if it's not factorable, we can use completing the square, never completing the square, right? We could use quadratic formula or square root property or something like that. If you're having trouble seeing the algebra through the trig, then let's just, simplify it. This is 2c squared minus the square root of 3c equals 0. Is this factorable?
Can you factor out a c?
We can factor out a c. And then this becomes 2c minus the square root of 3 equal to 0. And now I'm just going to put the cosine back in for c. The factored form of this is cosine times 2 cosine minus square root of 3 equal to 0. And at this point, we can apply our zero product property. We get cosine of x to be equal to 0, and 2 cosine of x minus square root of 3 equal to 0. Any questions so far? All right, well, now we have these two little linear equations to solve. It's basically the first problem we did. It's nice because there's a single trig function that's linear. So we're going to isolate that single linear trig function. In the first one, that's already done. So we're ready to say that x is equal to cosine inverse of 0. So we need to figure out where on the whole unit circle from 0 to 2 pi, where is cosine equal to 0? Now, cosine is equal to 0 here and here. Oh, we're going to get two answers for this first part of our equation. We're going to get that x is equal to pi over 2 and 3 pi over 2. However, for your test on Tuesday, the only answer you would give me if I asked you for cosine inverse of 0 would be the pi over 2. But it said the whole interval 0 to 2 pi, so I got to check the whole thing. Any questions on that first part?
So like for the other ones, it's just like the positive numbers?
Not necessarily. For the test on Tuesday, for sine, you're looking between negative pi over 2 and pi over 2. And for sine and tangent, you're looking from negative pi over 2 to pi over 2. And for cosine, you're looking from 0 to pi.
Okay.
All right, let's solve the second half here. We need to solve 2 cosine minus square root of 3 equals 0. We want to start by isolating the cosine. So we're going to add square root of 3 to both sides. And then divide by 2. Oh, if cosine of x is equal to square root of 3 over 2, that means that x is equal to cosine inverse of square root of 3 over 2. So the question becomes, where from 0 to 2 pi does cosine equal square root of 3 over 2? All right, well, I'm going to check out my unit circle. Square root of 3 over 2, that's the long side of our 30, 60, 90 triangle. Cosine has a positive value, so that tells us we have to be in either quadrant 1 or 4. Long side, short side triangle. That gives us a 60-degree reference angle. And then we have that same sister triangle with the same reference angle down in the 4th quadrant. We need to write our answers in radian form. So the one in the 1st quadrant, that's going to be pi over 3. And the one in the 2nd quadrant, that's going to be 5 pi over 3. So we came up with 4 answers. Questions, anybody? All right, let's try some more. We want to solve cosine of 2x minus cosine of x equals 0. Well, so we look at this and say, oh, great, they're both cosine. But the problem is they're not both the same cosine. One's cosine of 2x and one is cosine of x. That is different. So we need the arguments to be the same in order for us to do any type of algebra to it. It's always easier to tear down an argument than it is to build it up. So I'm going to look at that cosine of 2x and think that I want to apply a double angle formula to change the argument from 2x to just x. Well, if you look at your formula sheet for your double angle formulas, cosine has 3 different ones. Cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus 2 sine squared. Which of those 3 do you think would be the best one to substitute in so that we can try to solve the equation?
Probably the 2 cosine squared minus 1.
I agree with that choice. Why did you make that choice?
Because it's like because the other one mixes sine into it and this one just keeps.
Exactly. It's the only one that doesn't have some other trig function in it. And we want to have a single trig function to solve the equation. So we are going to substitute in for this. No. I'm sorry, I don't want to know what's wrong with my kids today. So there we go. Now we have something that is cosine x and cosine x. Also notice that one of the cosines is quadratic while the other one is linear. So that means this is quadratic in form. I'm going to want to set it equal to 0, put it in descending order, and try to factor it. This becomes 2 cosine squared x minus cosine of x minus 1 equals 0. And as always, if you're having trouble seeing the algebra through the trig, you can just strip it down. This is 2c squared minus c minus 1 equals 0. And we want to factor it. You can either use trial and error or your AC method. Out of this. All right. That looks good. Factors into 2c plus 1 times c minus 1. And now that I've gotten through the algebra, I'm going to plug the cosine back in. Anybody, any questions so far?
Yeah, does it matter if you use the square brackets versus like the parentheses?
Absolutely not. I just don't like the way it looks when I have parentheses around parentheses. I start getting confused with what goes with what, so I choose to use the square bracket. Anybody else? Now that we are factored, we can use our zero product property and set each one of these factors equal to 0. We're going to have 2 cosine plus 1 equals 0, and then our other one will be cosine of x minus 1 equals 0, and we'll solve each of these little linear equations. We'll start by isolating the cosine. So I'm going to subtract 1 and divide by 2. If cosine of x equals -1/2, that means x equals cosine inverse of -1/2. So we want to know where from 0 to 2 pi does cosine equal this -1/2. Well, if cosine is negative, that means that we have to be in either quadrants 2 or 3. And -1/2 is the short side of our 30, 60, 90 triangle. So short side, long side. That's giving us a 60-degree reference angle. And now we just need those two angle measures in radian. The one in quadrant 2 is 2 pi over 3, and then the one in quadrant 3, 4 pi over 3. Questions on that part? We also need to solve cosine of x minus 1 equals 0. Linear, so again, we're going to isolate the trig function. If cosine of x is equal to 1, then x is equal to cosine inverse of 1. So we want to know where from 0 to 2 pi is cosine equal 1. That only happens in one place. The only place that cosine is exactly 1 is right here. Now you got to be careful. I would glance back at the directions and see whether we're supposed to include 0 or 2 pi, because we know that this is both, right? 0 and 2 pi. So if we go back to the directions, it says include 0, exclude 2 pi. So I want my answer to be 0 here. So there we go, 3 answers. Questions, anybody? Next, we're going to solve 2 square root of 3 sine of 2x equal to square root of 3. Notice that we have a single trig function, so that's usually ideal, because we want to just isolate that trig function and then do our inverse trig function. But you'll notice with this one, it's different than the very first one we did in that the argument is 2x instead of just x.
I have a question.
Yeah.
So would you bring the 2 square root 3 to the other side and then do the double angle just on that sine 2x, or would you do it on the whole thing?
Okay. All right. So give me 1 second, Jordan. So we have the first option is just to isolate the sine of 2x and use the inverse trig function without ever going to the double angle formula. Our other option is to use the double angle formula. And the double angle formula only gets substituted in for this part. So it doesn't matter if you move the 2 square root of 3 first or do your substitution first and then move the 2 square root of 3. Doesn't make a difference. If you look at the double angle formula for sine, though, there's only one. And that double angle formula for sine is 2 sine cosine. And we don't want to introduce a second trig function if we don't have to. So I would opt against using my double angle formula here. Jordan, did I answer your question in that?
Yes, thank you.
So instead of substituting in 2 sine cosine, I'm going to isolate the sine of 2x. I'm actually going to write out the division because it's all these radicals. I don't want to make a mistake. So we're going to get sine of 2x equal to 1/2. Questions so far? Well, if sine of 2x equals 1, that means 2x is going to be equal to sine inverse of 1/2. But there's something extra we have to do here. Because the argument is 2x, You see, the directions say that x, our answer, is going to be in between 0 and 2 pi. Well, our argument is 2x. So if I take this inequality and I want to turn the middle into 2x instead of just x, I got to multiply all parts of the inequality. So that says that 2x is going to be in between 0 and 4 pi. So that means that, in the next step, we're going to say where from 0 to 2 pi does sine equal a half. We're actually going to say where between 0 and 4 pi is sine equal to 1/2. Basically, we need to go 2 trips around the circle when getting our answers. If our argument was 3x, we'd go 3 trips. If our argument was 4x, we're going to go 4 trips. If our argument is x over 2, we're going to go half a trip. If our argument is x over 3, we're going to go a third of a trip and only go 120 degrees. Right? So if you ever leave the argument and don't change the argument from 2x to just x by using some sort of trig identity, you have to go multiple trips around the circle. In this one up here, where we had an argument of 2x, we used an identity to change it to just x. So this multiple of trips around the circle wasn't applicable. Here, we're not applying an identity. We're keeping the argument of 2x, so that means we have to go 2 trips around the circle. Anybody have any questions on that? Now, of course, I really only just do the first trip around the circle, and then I add 2 pi to each of them to get the coterminal angles for the second trip around the circle. All right, well, let me draw my little unit circle here. Sine is positive 1/2. Sine is positive in quadrants 1 and 2. 1/2 is the short side of our 30, 60, 90 triangle. Long side, short side triangle. That's going to be a 30-degree reference angle. And then we got that sister triangle over here, 30-degree reference angle. So that's going to be pi over 6 and 5 pi over 6. This is only the first trip. Now we need to go a second trip around the circle. We'll get 2 more answers. But all you need to do is add 2 pi to each of these to get the next 2 answers. If I get 2 pi,
wouldn't it be 11 pi over 6?
I'm sorry. Go ahead, Alan.
Wouldn't it be 11 pi over 6 for the first trip?
It's not negative.
No, because 11 pi over 6 is going to put us down here in quadrant 4, and sine would be negative in that quadrant.
Oh, okay.
So our 2 triangles,
sorry.
where sine is positive in quadrants 1 and 2. So I'm going to take that 2 pi and I'm going to change it into an equivalent fraction with a denominator of 6. That's just going to be the easiest way to add it in. So 2 pi is the same as 12 pi over 6. So if I do 12 pi over 6 plus 1 pi over 6, that's going to be 13 pi over 6. And then 12 pi over 6 plus 5 pi over 6, that is going to be 17 pi over 6. Questions so far? the very last thing we need to do, see, we're trying to solve for x, not 2x. We now need to divide every single one of our solutions by 2. I'm just rewriting here what I had. So every single one has to be divided by 2 because we're solving for just x. Our final answers end up being x equals pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And those 4 answers do fall in between 0 and 2 pi. Questions? You will definitely be seeing one like that on the Unit 4 exam. Again, not what we're going to see on Tuesday. It'll be the one after that, but you know, that would be when I would start. Next, we want to solve sine of x over 2 equals cosine of x over 2. Notice that we have 2 different trig functions, and they both have arguments of x over 2, which is not our preference. Just x would be ideal. Anybody have any ideas on what we could do to better our situation? Possibly change the argument, hopefully change it into a single trig function.
The half angle, maybe?
Well, if you take a look at our half angle formulas, you'll notice that both sine and cosine, the right-hand side of the formula turns it into cosine of, well, x in our case.
Ooh, or could you divide it and then make it tangent? Divide the cosine over?
Huh. Yeah, you could. Nobody's ever suggested that, and I never thought of it either. Huh, let's see that. That might be better. All right, so that becomes tangent of x over 2. I don't know that I like this any better though, Jordan. I mean, let's look at it, but I don't know that it's going to be any better for us. All right, so I switched it to tangent by dividing. Tangent has 3 different formulas. We definitely would not want to use a formula that introduced a second trig function. So we would definitely want to use the one that has the square root, because that only has cosine. I'm just taking a look at something quick. Okay, you know what? I wouldn't even use this. Okay. So many options in math. All right, so we could use our half angle formula and turn it into the square root of 1 minus cosine over 1 plus cosine. Or we could do what we just did in this previous example here, that our argument was 2x, so we went twice around the circle. Here, we could keep our argument as x over 2 and just go halfway around the circle. And then I'll do it the other way too, because I'm not sure how many people would have thought to do this. So x over 2 is going to be equal to tan inverse of 1 because of the argument, only go 1/2 trip around the circle. So where from 0 to pi
Isn't it pi over 4 and 3 pi over 4?
well, hold on. Where from 0 to pi does tangent equal +1? Oh, tangent is positive in only the first and third quadrant. And since our argument is x over 2, we're only going halfway around the circle, so that would only give us the one in the first quadrant. And tangent is 1 when we have a 45-degree reference angle. So we are getting that x over 2 is going to be equal to pi over 4. But what we really need is to solve for x, so we're going to multiply both sides by 2 and get x equal to pi over 2. Oh no. Questions at all? Right. I'm going to do it the other way with the two double angle formula or half angle formulas, because I'm not sure how many people would have thought to switch it into tangent. I wasn't thinking that. So I'm going to substitute my two half angle formulas in for both sine and cosine. So we get plus or minus 1 minus cosine of x over 2 equals plus or minus 1 plus cosine of x over 2. Algebraically, what we have here is a radical equation. So I'm going to square both sides. Not only will squaring cancel out the big square root, but it also negates the plus or minus, because if you square a positive or a negative, you always end up with a positive. So this is going to give us 1 minus cosine of x over 2 equals 1 plus cosine of x over 2. We have a proportion here. We can cross multiply. Two times 1 minus cosine equals 2 times 1 plus cosine. 2 minus 2 cosine equals 2 plus 2 cosine. And now we're down to something that's nice. It's linear cosine of x. So let's get our cosines together and our constants together. So I'll move this over here with those ones and move this over here with that constant. It's going to leave us with 0 is equal to for cosine. Isolating the cosine, we'll divide both sides by 4. That's going to give us 0 equals cosine of x. So x has to be equal to cosine inverse of 0. So that means we're looking where on the unit circle is cosine equal to 0. Cosine is 0 2 spots, here and here. Pi over 2 and 3 pi over 2. Well, you may be thinking, hey, Allison, there's only one right answer in math. How did I get a different answer using this technique than the other technique? It's because we're not done with this technique. See, during our solving process, in the very beginning, we raised both sides of our equation to an even power. Anytime you do that, you have to check your solutions. And when you check your solutions, you're going to find that 3 pi over 2 does not work. See, if we plug in pi over 2, it's asking, well, is sine of pi over 4 equal to cosine of pi over 4? And it is. They're both positive square root of 2 over 2. But when we plug in 3 pi over 2, our arguments become 3 pi over 4, and sine of 3 pi over 4 is positive, while cosine of 3 pi over 4 is negative. So we have to throw out that solution, and we're left with just the one. Either technique, both great. Questions, anybody? You'll notice that the, hold on, I want to see how much we got here. I just want to check our calendar because I don't want to do so much that we don't have anything to do next time.
So next Tuesday is our test, right?
Yeah.
Do we have like a specific time period, or is it like any time during the day?
I just posted an announcement in D2L. It'll become available at 12 a.m. on Tuesday. So that's really like, depending on how you want to look at it, midnight on Monday night.
Mhm.
Right. So 12 a.m. on Tuesday it'll open, and Wednesday at 11:59 p.m. it'll close. So it's actually like a 48-hour window you guys have to take it. There's 2 attempts. I will take the best out of the 2 attempts, but I'm not assigning any partial credit. I will look for like glaring syntax issues, like if you wrote x equals when you weren't supposed to write the x equals, but you had the right answer, I'll give you credit for that, but not partial credit, just syntax issues. Alex, what was your question?
And this is on Pearson?
Yes. Anybody else? All right, I want to do a couple more. But you'll notice the directions have changed here. Now they're asking us to solve each equation for the solutions over the interval 0 to 360 degrees. Round the solution to the nearest tenth is appropriate. So it's giving us degrees. Now all of our answers should be in degrees. We want to solve cosine equals sine squared of theta over 2. Now when I look at this equation, I see double trouble. I see 2 different trig functions, and I see 2 different arguments. I would like the same trig function and the same argument. Any ideas?
Would you do the power reducing one first?
Jordan, you're coming out of like left field with all these things. Yeah, I guess we could. That's not what I was thinking, but sure. Okay, let's try that. So I can do power reducer for sine. Our power reducing formula says sine squared theta equals 1 minus cosine of 2 theta over 2. So this is going to turn into 1 minus cosine of 2 times theta. Now our theta this time is theta over 2. And that worked out really nice. I would never thought to do that. So this becomes 1 minus cosine of theta all over 2. I just want to point out, so this is power reducing here. Say I used half angle instead. So if we used half angle, this would be cosine of theta equals, now remember sine squared of theta over 2 is the same as sine of theta over 2 squared. So I'm going to use my half angle here. And then all that squared. And then when I actually square the right-hand side, squaring a plus or minus negates it, and then squaring the square root, those are going to fall out. You see, I end up with exactly the same thing, whether I use the power reducing formula or a half angle formula in the beginning. So either one, both great. All right, let's finish it up. I'm happy to see cosine of theta is the only trig function I have, so both linear. We want to get all of our cosines together, but the first thing I'll do is get rid of this fraction by multiplying both sides by 2. So 2 cosine is equal to 1 minus cosine. Continuing to get all my cosines together, I'm going to add cosine to both sides. It's going to give us 3 cosine is equal to 1. Now that I have all my cosines together, I'm going to isolate that cosine by dividing both sides by 3. Cosine of theta is equal to 1/3. It follows then that theta is going to be equal to cosine inverse of 1/3. Questions on anything I've done so far? All right, so 1/3, is that a number that's on our unit circle?
No.
No, it's not. So that means that we're going to use our calculator. So if we plug that into our calculator, what do we get for theta?
I got 70.53.
Anybody else get that?
We need to be in degree mode, right, on our calculator?
You are correct.
Okay, good.
Can anybody confirm that? Oh, yeah, okay, I can. I see it in my notes. All right, are we going to nearest hundredth? 10th, nearest 10th. So let's call it 70.5. I mentioned on Tuesday that our calculator only gives us one answer ever, right? It's using the pure definition of our inverse trig function. It never gives us the sister triangle, ever. So what we need to do, because the directions said find all solutions from 0 to 360 degrees, is to find the sister triangle. Now, all our sister triangles, right, they always have the same reference angle, right? If we go back and look at all our pictures, right, they both have a 30-degree reference angle. They both have a 60-degree reference angle. They both have a 60-degree reference angle. So our sister triangles, they always have the same reference angle. Well, they're giving us this angle here in the first quadrant with a 70.5 degree reference angle. Which other quadrant is cosine positive? That would be the fourth quadrant. So we also need this angle here down in the fourth quadrant with a reference angle of 70.5 degrees. What is that second angle going to be?
$289.5.
And how did you come up with that?
I subtracted 360 by 70.5.
Perfect. And there we go. So we reviewed this topic in pre-calc, and my pre-calc class, man, both of them on a take-home quiz got kind of crushed on these types of questions. Because we were getting decimals, they felt uncomfortable because we were getting these thetas that were decimals. Like 70% of them did not find that sister triangle. So make sure you're always finding the sister triangle if the directions tell you to solve the whole unit circle. How to find that sister triangle. All right, let's do one more today, and then we'll call it a day. Yeah, that's a good one. All right, tangent of theta plus 1 equals square root of 3 plus square root of 3 cotangent of theta. Oh, right away, I see that I have two different trig functions, and that is not my preference, right? We always want to get it in terms of the same trig function. And I'm trying to think of some kind of identity that relates tangent and cotangent. My first gut is to think of a Pythagorean identity, but the Pythagorean identity that involves tangent has secant with it. So I can't use a Pythagorean identity here. Are there any other identities that you know that relate tangent and cotangent?
Yeah, can you do change the tangent to sine over cosine and change the cotangent to cosine over sine?
We could do that, but that's going to create a little bit more work for us than another option. What's another option to relate tangent and cotangent?
Can't you just do 1 over 10?
That's it. We're just going to switch cotangent into 1 over tangent so that everything is in terms of tangent. Jordan, you're not wrong. It's just going to be a little bit longer route to do what you suggested. So this becomes square root of 3 over tangent. Well, I'm happy that everything's in terms of tangent, but what am I not happy about?
Aren't you going to end up having tangent squared on the other side, and we're going to have to do the power reducing?
Okay, you're like 4 steps ahead of me. And yeah, I see you are a lover of power reducing formulas. I like have never used a power reducing formula before. Outside of Calc 2, I've never used a power reducer. But well, what are you talking about? Can you give me more to the story?
So we're gonna have to get the tangent on one side so we can isolate the variable. So I was thinking of just multiplying. Well, that wouldn't work either because you'd still get square root of 3 over tangent, right?
I don't know. You didn't give me your whole thought.
You'd still be left if you multiplied everything by tangent, you'd still be left with it on both sides. So that wouldn't really.
Well, who cares if it's on both sides? We can always move that, right?
Yeah.
All right. So what I don't like about this equation, right? I said that I like that everything was in terms of tangent and theta now, but what I don't like is that the variable I'm solving, theta, is located in the denominator. So anytime the variable we're trying to solve for is located in the denominator, it's super high priority to get it out of the denominator. And the way we do that is by eliminating the denominator altogether. We'll eliminate the denominator altogether by multiplying everybody by tangent. Distributing that tangent on the left side gives us tangent squared plus tangent equals square root of 3 times tangent. And then here's where they cancel out and we're out of the denominator. Questions on anything we've done or why we've done it? Okay, well, algebraically, what kind of equation is this? And again, it'll be helpful to take all the trig stuff out of it. This is t squared plus t equals square root of 3 times t plus square root of 3. What kind of equation is this?
Quadratic.
It's quadratic, and we know because we got that t squared. So anytime we have a quadratic equation, we like to set it equal to 0. Try to factor it if we can, and if not, we'll use another method. T squared plus t minus square root of 3t minus square root of 3 equals 0. We want to try to factor it. Oh, by the way, yes, I do realize that these are like terms, but when you have an integer is one coefficient and the radical is another coefficient, it's not so helpful to combine those like terms. Maybe in some high math classes, okay, fine, but we definitely don't want to do that.
Factor by grouping.
We have 4 terms, so that tells us that we want to factor by grouping. We have a GCF of t out of the first 2 pairs. And then a GCF of negative square root of 3 out of our second 2 terms. And there's that common binomial factor that lets us know we're on the right track. This factors into t plus 1 times t minus the square root of 3, still equal to 0. Questions at all on the factoring? All right, I'm going to put my tangent back in. Tangent of theta plus 1 times tangent of theta minus square root of 3 is equal to 0. And now we're going to apply our 0 product property and set each of these factors equal to 0 and solve. So the first one, we get tangent of theta is equal to negative 1 So that means theta is equal to tan inverse of -1. We're looking for where on our unit circle is tangent equal to -1. Tangent is negative in quadrants 2 and 4. Tangent is when we have a 45-degree reference angle. So our angle in quadrant 2, 135 degrees, and then our angle in quadrant 4, 315 degrees. And then we have our other equation to solve. Isolating tangent, tangent is equal to square root of 3. So theta is going to be tan inverse of square root of 3. So I need to figure out where that's happening. Square root of 3, that's when we have square root of 3 over 2 divided by a half. So y's got to be square root of 3 over 2, and x has to be a half. Tangent's positive in quadrants 1 and 3. So x is the little side, y is the big side. We're looking at a 60-degree reference angle. So theta equals 60 degrees and 240 degrees. And those are our 4 answers. Question, anybody? All right, well, that's all I want to do today. Reminder that, well, there was a quiz, chapter 5 quiz due last night. If you didn't get it in last night, please get it in today. And then the 6.1 quiz is due on Monday night, as well as the My Math Lab homework, and the bonus quiz, I think, is due at 8 a.m. on Tuesday. So if you have any questions on anything, please don't hesitate to give me a call. Also, a reminder that my office hours that I typically have on Monday nights will be shifted to Tuesday night next week, just because I have another meeting I can't get out of on Monday. I will make an announcement, post an announcement in D2L about that as well. Anybody, any questions about anything? Just a reminder, you can email me questions anytime, and if my posted office hours aren't working for you, just let me know and we can do by appointment as well. Usually I don't like to do mid-afternoon because after I teach, I try to do something in the afternoon, but I'm certainly available. All right, if nobody has anything, have a wonderful day.